systems, you can begin your presentation.
Okay, thank you. So hello and good morning. My team and I will be representing Terminus Systems. We're a company that we made to solve the end effector inverse kinematics project for the semester. This is our team. My name is Andrew, and alongside me today, we have Richard, Samson, and Igor. After meeting with our client, we summarized our needs into this problem statement. They needed us to design an end effector and program the inverse kinematics for a 3D printed mechanical arm that had 3 degrees of movement. This arm was meant to perform manual tasks on a naval ship that could potentially reduce the manpower needed. These tasks could range from sandblasting to power washing to inspection or painting. Here's a demonstration of our arm working with a prototype on the end.
Hi, so now I'll be touching upon the other aspects of our design. So with the inverse kinematics, the way it works is you are able to put in the set coordinates you need to move to, and it will do all the inverse kinematics calculations, and then you can start the movement. With the end effector, we have mounted a camera on it, which will allow, due to the limitations of the hardware we could get within budget, a slow updated feed of images, but not necessarily a video live stream. And you can also take pictures while it is showing the images that will save onto your computer, which is shown at the bottom here. On the right, we have also an ultrasonic sensor. Here we just have a simulation of it running. And the idea is that we wanted to prioritize reliability and safety at the budget we had. So because we have a known distance and length of our end effector, the ultrasonic will sense the surface that the end effector is working on, allowing it to sense whether it is out of reach of the end effector. If it is out of that reach within a small margin, the idea is that it will notify the user that that an adjustment needs to be made. If it's larger, then something wrong has happened. It's been shifted by someone, it hit something, and it causes it to stop. So now we'll show our prototypes that we had. This is just a quick showing of our iterations of our prototypes and the CAD models. And now we'll show our final design. So here you can see, for now we used a marker. We initially planned a pump, but we decided we'd like to prioritize safety and reliability over showing that we can turn a pump on and off, whereas the inverse kinematic solution would stay the same. And here we have some more images showing the ultrasonic sensor in the camera. The ultrasonic sensor can measure to 3 meters, and we have a 0.3 megapixel camera for a semi-live feed. And that is all. So we're opening the floor to questions now.
Yeah, I'll jump in first. Thank you guys. Good presentation.
Thank you.
I wanted to ask a question right about the starting at the very beginning, and I'm wondering what kind of research did you do to better understand the context for the solution, and how did that impact the ultimate design?
So we were able to meet with the client multiple times, and on major iterations of our prototypes, we were able to get updates and opinions, thanks to Theo, on whether this product was what the client was looking for or if changes need to be made.
Can you think of an example of something that you learned in that research that forced you to, kind of change direction or adapt somehow?
Not necessarily. We did have the initial problem change quite majorly halfway through. Originally, we were supposed to design an entire arm, and then it was changed to creating an end effector and inverse kinematics solution that would run on a test rig that was made for the whole class. So necessarily a change, I wouldn't say so, but different prioritization of what we had to do, for sure.
Thanks.
Okay. Can I raise some question? Okay.
Okay.
First
Yeah,
of all,
Fernando.
yeah.
Go ahead. Yeah.
My nickname is Andy. Okay, so you can actually call me Andy. Okay. First and foremost, congratulations, guys, for uh, a very good solution to the problem that you have. Okay. So, question. Did you base your solution to any existing commercial off-the-shelf products out there?
Yes, so
Okay.
all the code was made to run on a Arduino. That's also, however, with our testing examples, that's why we weren't able to show the end effector on the ARM itself, because it was a test rig for the whole class. We weren't able to do soldering joints and things like that. So that's why we had the separate simulations. But so it runs on an Arduino. It runs on an Arduino ultrasonic sensor. And we have a OV7670 camera for our design.
Okay. Actually, my second question, my follow-up question to that one is, did you ever try to look into, since the idea was solving the kinematics, okay, and you proposed for a 3 degree of freedom, a robotic arm,
Yes.
did you ever try to calculate, for example, what would be the extent, what would be the area that the robotic arm can actually do? Did you adjust any of the arm for any of your calculations to say, for example, for painting, for example, 1 square foot?
Yes. So the TAs gave us good information on the test rig that we were given. And it was just a case of inputting the correct lengths, distances, and variables and angles of range into the program itself. Does that answer your question?
Yes. So basically, the solution that you had was mostly an automated one. Yeah, correct. Because I was, yeah, when you have 2 arm, for it to extend, for example, you need to calculate, for example, the angle before you can actually put in, for example, a motor, stepper motor, for example, of what degree. So yeah, I think, yeah, okay.
So I have one question. So for the solution that you selected for the problem that you stated at the beginning, based on your test results and what you got at the end, and probably based on the feedback from the client, how you are sure that you fulfill the requirements of the problem, or you solve the problem, basically? What's the main indicator that the solution actually will fulfill the requirement?
Well, the idea was that we needed to have a functioning inverse kinematic solution, which we have. And we were able to demonstrate that through the movement of our arm and that it worked as intended. And we also added extra safety features that were not necessarily a requirement, but highly encouraged. So we feel that we hit all the individual points that were told to us by the client and professor.
Yeah, that's great. Yeah, this is actually a great presentation, and I just want to thank you. Great work.
Thank you.
So thank you, Team C5. Judges, any more questions? Or we can go ahead with the next team. Okay, thank you, Team C5. So we'll go with the next team, C3. Can you share your screen, please?
We can start whenever. Okay.
Yes. Judges ready for the presentation? We can start. Okay. So your time starts now.
Right, so hello, we are Group Armageddon, and we'll be presenting our inverse kinematics robot solution. All of us with masks on are on campus right now, and Rebecca is at home. So our user Sam is fresh out of high school with little technical experience and decides to join the Royal Canadian Navy. Aboard the Halifax-class destroyer, Sam is put to work removing rust off the walls using sandblasters, vacuums, and paint sprayers, a tedious and time-consuming task that our solution solves. We were tasked with programming a robotic arm using inverse kinematics and designing end effectors to perform various tasks. We are confident our team has the solution that exceeds our clients' needs. Our open source scalable code uses the lengths of the robot's arm and desired coordinates to solve for the angles needed. The stepper motors can then move with 3 degrees of freedom to different positions. Our marker end effector draws shapes on a surface based on coordinates inputted. It is a proof of concept for the client's need to sandblast or water blast a gridded area. Our camera end effector continuously takes and saves pictures of the area to scan them in our corrosion detection code. The camera scans the space using a grid in the Cartesian plane, where each square on the grid corresponds to a set of coordinates. The camera moves from square to square, taking a picture each time. Once the camera has taken a picture of every single square, all the images are imported into our corrosion detection software, where they're classified as 1 for corroded or 0 for not corroded. The code is written by Ben Zager and uses hue saturation and edge values around the detected hue to classify the pictures. Now let's take a look at how Sam can use our solution on his first day on the job.
First, Sam needs to scan the area for corrosion. So using the simple user interface, he selects the camera end effector button, opens the camera interface file, and begins to run the code. The code tells the robot to move to take a picture in each grid. The camera interface shows a feed of the incoming pictures. To demonstrate, Sam will take a picture of a non-corroded object and a corroded object. Notice the picture is being saved to a folder on the computer. Then the corrosion detection software runs and outputs the name of each corroded picture, where each picture corresponds to a number on the grid. Sam can use these coordinates to remove the paint of the corroded areas. As a proof of concept, Sam can choose from 3 shapes to draw. They use inputted coordinates to draw shapes on the provided surface. But to prevent Sam from being injured, our infrared sensors trigger the LED light and buzzer that interrupts the motion of the robot. Sam can also use the emergency stop button on the user interface if a malfunction occurs.
Our only expense is the camera and the sensors. Other items were obtained for free, helping us stay under our $50 budget. And as a group of engineers with little programming experience, a software-heavy project proved a big challenge. Nevertheless, we incorporated the client's feedback and went the extra mile and implemented a corrosion detection AI. We created a fully automated solution with all working parts, and with more time and a larger budget, we would fully integrate all the parts into one program to present the perfect solution. Thank you.
Okay. Good morning. Okay. Congratulations on again for your very good solution for the problem at raised. Okay. One question to your team. You actually stressed more on the sandblasting and pressure that is actually on the front end of your robotic arm, correct? Did the client ever provide you information of the pressure on the front end side? Because when you paint, of course, you have air pressure going out. You also have force that will be coming out from a sandblaster. Did you try to consider that particular variable into your equations?
Yes, we did, but we can only do it to a certain degree because we were given the robot. We didn't actually make it. So we could only implement that into our end effectors. So we first originally had a clamp end effector that would hold these sandblasters and whatnot, but we couldn't really prove anything. So that's why we decided to go with the marker. So we could, show that we could put in coordinates and it can do different functions of whatever you want to do.
Yes. Okay. So right now, the table that you're showing us is the weight supported by the end effector maximum will now be 1 kilogram. So if you're going to convert it to a force, will that be sufficient enough to, hold the entire robot in place when you're going to put a sandblaster in front of it or paint?
We weren't
Something?
given any specs of
Okay.
which kind of
Okay.
sandblaster, so, but we can
Yeah,
only do it
okay.
to a certain degree with their end effectors. So yeah.
Okay. Thank you. Thank you.
Anya, do you want to go?
Uh, no, just go ahead. Yeah.
Okay, sure. Thanks, team. I really like the user story that you added at the beginning and at the end of the presentation. So my question is, I was wondering if and how you considered the role of the environment in which it's going to be used, and what decisions that situation presented to you, what changes you made based on understanding the environment in which this is going to be used.
So from the beginning, we understood that it was going to be used on a boat where water is definitely present and it's always an aspect that we have to consider. That is why we chose to enclose our end effector to prevent any water from getting on the wires and such. So that's what we considered in that case. And as for our other end effector, it wouldn't really pose a problem necessarily because it's using the sandblasters and the the remover of the corrosion and the paints, which is already used on the ship. If I understand.
Is your understanding the ship would always be in dry dock? This would never happen, and they'd never use this tool when the ship is at sea?
We were actually told by the client to consider it that it was always used just docked.
In dock, okay.
Yeah.
Yeah, nice, thank you.
So I just want to add great presentation and a great user story. It's actually, helping to basically tell the story where you came from and why you choose this solution. The question I have is in terms of electronic and storage, because you are saving so many files because, the grid, every time the camera take the picture, the grid will be filled. And so how do you solve that kind of challenge? Like in terms of, storage space for electronics, because this will be remotely, and then
So we assume that after each use, the pictures are also deleted once the task is done. So it resets new every time. And also we can use an SD card to put the pictures on as well, which is a form of external storage.
Okay. All right, thanks.
Judges, I want to know, are you inputting your what is it called?
Comments and
ratings.
Yeah,
ratings. Yeah,
you're already doing
exactly.
that?
Yes, we are doing that as we go. Yeah, at least for myself, I can say.
Perfect. Thank you.
Welcome.
Thank you, team C3. So I think we can proceed with next team C1. So team Chem Engineering. So could you share your screen, guys?
Sorry, I don't know what happened when I turned my video on, but my formatting wasn't working. I couldn't interact with the Zoom. I'm going to share right now.
Okay.
Are we good to go?
Ready?
Yep.
Okay.
All right,
So
so
your time starts now.
So we're Team ChemEng, and we'd like to present you our solution for the project we've been given this semester. So as you know, we were tasked with creating a creative inverse kinematics program that can safely pilot a robot in 3 degrees of freedom. And it wants to be able to work cohesively with multiple end effectors that can be switched easily. And we need it to be operated by one single low-skilled user. So in meeting with the clients, we've generated this list of needs. Most notably, the arm needs to be safe, it needs to be easy to operate by one user, and it's got to have a simple interface to interact with. So to meet this, we came up with our light and camera end effector as the end effector we decided to focus on. It's got a camera, LEDs, and an ultrasonic sensor built into it. The camera is meant to scan the workspace to be sent towards the UI, and then the depth sensor is there for safety features as well as so it knows where it is. But the depth sensor has a reading of distance, and as the distance decreases, meaning it's getting closer to whatever is in front of it, lights will begin triggering on the side to alert anyone around of potential impact that could happen. And as the distance comes within 4 centimeters, the end effector will send a signal to Windows Kinematics to tell it to stop the forward motion. And here are some pictures. You can see the camera in the middle of the end effector, the depth sensor up top, and for now the lights are along the side of the end effector.
For our inverse kinematics, we decided to take custom-made modules. You can see it's named coordinates. You input the desired coordinates, the X, the Y, and the Z, and it will output the angle that the motors need to move to. In these for loops, you can see that the angles are then divided by 1.8 because that is the step size of the stepper motors that were given. This makes the motors in the X, the Y, and the Z direction step the amount of steps they need to get to the desired position. Here's a quick video of the arm functioning. Here you can see it moves in the Y direction, it moves in the X direction, and finally in the Z direction. Here's a quick video of our UI. It opens up in the search bar where you're able to search for whatever photo the camera has taken, whatever its name. You can backspace to make fixes. Here you can highlight your workspace that you will get the coordinates. You can clear your highlight. Here's the emergency stop on the UI. The drop-down menu can be open and closed, and you can reopen the search and reopen whatever photos else that you would like. Thank you for listening, and that's our presentation.
Are there any questions from the audience?
One question. What camera did you utilize for taking pictures?
It was just a very simple, I think, 50 millipixel Arduino camera. It was just like the camera that was able to integrate with the Arduino.
Just something simple to fit within our budget, and we just use it as a proof of concept.
Okay, so in the future, try to consider also some aspects of your camera, like for example, the lens for focusing, those ideas, because if you base it from your picture itself and you have a user on the other end, that will determine the area for it to be, for you to implement whatever action. Quality is actually the key to do it, and basically the camera that you utilize will not have those additional options. Might only be a standard, I don't know, camera. Okay, so
yeah. That's also why we had the depth sensor, because that would allow us to have, say, that depth perspective in our calculations and our work.
So that's the thing. You have a depth sensor and you have a camera. If you're going to utilize your depth sensor, your camera will go near, right? Now the focusing will now be off. So do you get the idea on how those two things are being utilized? You have a depth sensor that measures distance, and you have a camera that should also have its own actuation for the focusing, so that you'll have a very vivid picture of what you're going to get. Okay, so that's it. Thank you. Thank you.
Thank you, team. Really good presentation. I liked seeing that you started to dive into the user interface a little bit. I wanted to talk a little bit more about that, and wondered, you showed some limited functionality in the interface in your demo. If you had the opportunity to continue to flesh that out, what other kinds of functionality would you put into that interface?
Well, with more time, we would have had the rust remover as well as the painter or the sander, I guess, depending on what we decide to go with. So that would be implemented in the interface, some kind of control system for that as well, that's kind of why we had the area highlight, because then we were able to have that area work with, and that's when we would create the coordinate system for the sander, the sandblaster, or the airbrush painter.
Gotcha. And were you able to share and interact with the client and experiment a little bit with that interface?
No, we didn't really get the interface sent to the client, but we did have some people, that weren't necessarily part of the creation of the interface to use it and utilize it and to test it out. So we would be able to tell how simple it is, how complicated it is, and whatnot.
Great. Awesome. Thank you, guys.
I'll just say thank you. Great solution. And also just a question about the limitation. And so you did demonstrate in your demo the X, Y, and Z movement of the arm. Is there any limitations that you have as a challenge that like the camera mounted on the arm has any limitation to reach out to different spaces? Yes, I know that you have the deep depth sensor, but is there anything else that was challenging in this solution?
I think it was kind of like the weight of our end effector, right? Because if we had made it too heavy, the arm would not be able to move, say, up or out as far as it could, especially because of the way the arm was put together. It was kind of just slotted together instead of, say, screwed together or drilled together. So when it moved out to the farthest reaches that it could, sometimes it would tip or, have some kind of issues with movement.
Okay, thanks.
Thank you, team. So we'll go ahead with the next group, C4, Swarm. So could you please share your screen?
Yeah, we're sure should be sharing it soon.
So judges, are you ready?
Can everyone see it? Just before we start? Okay. Just making sure my
So
camera
you
is on.
can start. Your time starts now.
All right. So my name is Aham. I'll be representing Team Swarm today in our robot arm presentation. So who are we? We are Swarm. We consist of Shahryar, Washira, Aham, Akam, and Matthew. Our group's main mission was to create a inverse kinematic robot, which was meant to clean up and paint over the Halifax-class destroyer ships. Our main goal that we sought after was to solve our client's problem. In doing so, we did have a problem statement laid out for us, which was to create a robot arm, an inverse kinematics solver, which was lightweight, efficient, as well as portable. But not only that, it also had to include an interchangeable end effector, something that can simply be taken off and replaced by another to perform a certain task. Next slide, please. Throughout the entire project, we decided to follow the concept of engineering design phases, which follows these steps. Empathize, where we try to understand how our client and or user is feeling. Define, where we create a problem statement that we will follow throughout the process. Ideate, where we create many different concepts for the project. Prototype, where we create certain parts of the final product through different prototypes. And finally, test, where once we completed our final prototype, we use the product in action to see how it performs. Next slide. Our group extensively worked on what we believe to be the best version of our product yet. This is our final design. We went for an adjustable clamp that would allow us to slide the piece into the mount and tighten the clamp as needed to ensure the piece is held down safely. The arm itself is a simple arm mechanism, allowing for the full 3 degrees of freedom motion required by the client. Obviously, there will be safety concerns on a project such as this, which is why the team opted for the simple safety measure of an emergency stop line, provided on the base of the arm. We also planned on adding sensors capable of detecting what we would consider unnatural movement, allowing for the device to stop, but unfortunately, budget constraints did not allow for this. We have even provided a fully functional simulation, so you're able to view exactly how the robot arm would move in real time. The next slide, please. So this right here, in the simulation, we demonstrate how the robot's going to move when in practice. As you can see, the arm movements are quite fluid and clean, so there should be no issue in the way the robot moves. We also simulated the end effector and how the clamp mechanism works. With the use of springs in the effector itself, it'll have elastic properties, allowing it to have a strong grip. Alongside the current design, we also have some main safety features. Next slide, please. So in the end, our plan has always been to create something that was cost effective and reliable. That was always our problem statement from the very beginning. We have been able to provide a great example of something very reliable for the robot arm, something that has many simple features and can easily be replicated. We are confident in the product, and we have created it simply because of its simplicity that we believe it will be a great product. So next slide. And that's it. Thank you very much. The floor is open for questions.
Thank you, guys. Loved seeing the design thinking coming into your project, and my question is really about that. And I'm wondering if you can just talk really briefly a little bit more about both the first and the last stage of the design thinking process. What did you learn at that empathy stage that guided your design direction, and then similarly, what did you learn at the end in testing around what you might change in a future design?
So when it came to empathize, luckily we were very fortunate to have many sit downs with our clients. We did go through extensive prototypes, and we understood from our very first meeting that the client was looking, at the very first, it wasn't very clear if we had to work on the arm or the end effector itself, but that cleared up along the way. But we did know that the main thing that he was looking for, our client, was a robot arm that had 3 degrees of freedom, included inverse kinematics in the arm. And that is exactly what we sought out for. We put that as our #1 priority. So when it did come down to what we set as our main priority, we did set that the inverse kinematics as well as the 3 degrees of freedom would be our #1 important thing that we would be looking out for in our research. When it came to testing, unfortunately, because the team is very dynamic, we do have a lot of time constraints. Many of them are even from outside the city, so it didn't allow for physical testing, but we did have the simulation, and it did provide us with exactly what we needed, which was how the robot arm would move, and that is that exact 3 degrees of freedom, as well as how our end effector would work. So when it came to testing, we were very happy with our result, after having worked extensively on the product itself.
Okay.
Okay.
Congrats. Hello. Yeah. Sorry.
Hi.
Okay. Congratulations. So most of the presentation was more on the end effector, and your end product was for you to be able to, for the end effector to be able to interact with objects. Was that right?
Yes.
How do you actuate that? What will be the actuation for the effector to interact with objects externally? Or was it that the effector will just be, will there be a user that will interact with that effector for it to be a multi-purpose
So
connector?
yeah, as mentioned in the slide 5, I believe, when we talked about our physical prototype and our final product, we did mention that our main thing that we wanted was basically it was just a simple clamp system. We wanted it to be very simple because we knew that sorry, not the clients, but the users of the product itself wouldn't have the greatest background when it came to technological aspects or even robotics.
Yes.
So it was our main focus was to try and keep it simple. So it was simply just pretty much just a simple clamp system. So our main end effector, basically that's just how our end effector works, is we just have it as a simple clamp system. That way it can be removed and inserted, and another end effector can take its place to perform another task.
Okay, so just a follow-up question to that one. So meaning, did your end effector, was it sufficient to all, let's say, attachments that the client actually had discussed with you before? Well, can it be attached to, let's say, a paint system,
Mhm. We
sandblaster? So would that
we
did
did run through those many possibilities. We even did include that in our
yes?
first draft when it came to our bill of materials. Unfortunately, because of certain constraints, the only thing that we could really do in terms of an end effector was something that can hold a blaster or a excuse me, or a like sander.
Yeah. Okay. So
But
thank you. Yeah. Just a suggestion. Try to delimit what will now be available, what will now be okay. But yeah, very good. Thank you for the answer. Okay.
thank you very much.
Yeah, I do have a question. First, to say it's a really great presentation. And also, I like how you guide us through the design process from very beginning to the end. The question I have is, you mentioned a few times during presentation the budget constraints, and what you would do, like what would be in your mind if you would have a better budget or not that much constraints? Like what other solutions would come to your mind as a team to have this better? Because this solution is also good even with constraints, but I know that you mentioned few constraints and like as you would go with something much better.
Yeah, I understand. So when it came to the beginning budget, honestly, if we had the starting budget, we would have been able to have the multiple end effectors that we prototyped in the beginning, because our first prototype included the entire arm as well as some form of claw, an airbrush, the basic necessities for this robot arm. But throughout this semester, we understood that the budget was decreased. But if we did have that budget, I believe our main goal would have been to focus on the multiple end effectors that we could install and remove. For instance, like ultrasonic sensors, high quality cameras would probably have helped, considering we do understand it is very important when it comes to a task like this. When it comes to painting, sanding, you do want the area to be very specific. So when it came to that, if it comes to the fact that if we had a better budget, we would have been able to actually incorporate extra features that would have ultimately helped the project.
Yeah. And that's great because, you have all these ideas. So, my suggestion would be just when you basically, this is good way of doing it to the client, just to have recommendation for the future solution or improvement of this current solution.
Yeah, we did
So
have
that's
very
great.
ambitious goals, but in the end,
Yeah,
we
exactly.
were at least able to produce something. So
Okay, that's great. Thanks.
thank you.
So thank you, team C4. Let's go ahead with the next team, C10, the last end effector.
Yep.
So team, can you share your screen?
There it
Judges, are you
is.
ready? Okay, so your time starts now.
Hello, judges. Thank you for coming. We're Team C10, or the last end effector, and this is our pitch. Our clients are looking for a 3-degree of freedom robot arm with an inverse kinematics algorithm able to determine motor angle based on coordinate input, as well as an end effector to water blast and repaint to grid area, all with adequate safety features. We developed an analytical solution to the inverse kinematics problem using triangular plane projection. This means that the angles are absolutely accurate and there are no approximations. Equally, our solution can detect whether the coordinate input is in range of the robot arm. Based on the hundreds of test cases, we currently have an average runtime of 1/100th of a millisecond. Finally, our solution is scalable to higher degrees of freedom and size without the need for a stronger computer. Our user interface, as seen on the slides, has an area for end effector coordinate input, a row of check buttons to control the attachments, and a high visibility emergency stop button. After the send button is clicked for the coordinate input, the values are run through our algorithm, then motors move to whatever position is relayed. To control the attachments, the user must simply click on the desired box to turn it off, then click again to turn it off. The emergency stop button, once clicked, instantly deactivates all motors and attachments, displays a message with first aid information, then seamlessly resumes activity after the emergency. Finally, our interface can relay information back to the user based on how they interact with it. When the user inputs coordinates outside the range of the robotic arm, it lets them know and it prompts them to try again. If the emergency stop is hit, after everything has been shut down, a message pops up with information about first aid location and procedures. Our end effector follows a completely modular two-pronged design that lets the user easily switch between tools depending on the job. We have developed 4 fully functional tools: a water blaster, a water vacuum, an LED light, and a drawing tool. Our design is strong as it doesn't lock the customer into one functionality either, but rather allows them to use this robot for any purpose with very little extra development. For example, the addition of a camera or IR sensor would be as simple as making it fit into our universal holder, like we did the LED or drawing tool. Here's a quick demonstration of how our robot arm works. So here I am inputting the coordinates into the end effector, the user interface. I click send and off it goes. Next, I turn on the LED light and I turn on the water blaster and it starts doing both those things. Next, I hit the emergency stop, everything gets shut off. Then when I click out of the emergency, activity is resumed. So from the left to right, we have the vacuum to suck up the blasted water, the drawing tool to paint the ship, the LED to work in the dark, and the water blaster to remove rust or debris. We believe that our design is best fit for the customer as it exceeds all of their needs. All of our code is written in Python rather than multiple languages, making it very easy to use and to debug. Our algorithm is so efficient, it can be run on a microprocessor. Our modular design allows the customer to use the ARM for all current and even future needs, and it's fully scalable to higher degrees of freedom while still maintaining plenty of emergency features. Thank you for your time and attention. The floor is now open to any questions that you might have.
Okay. Congratulations to your presentation. Very good inputs. Feedback mechanisms. Did you include any feedback mechanism aside from, as what you've seen? You have a user interacting with your UI, and feedback will now be utilized by the user itself. Did you think of any other solutions to provide feedback?
No, so the main feedback, the two ways that the robot arm can fail is either there's an emergency, which it will instantly get shut off, or two, the coordinate input is outside of range. We equally at one point had a user feedback for when you put in your angles, it will run it through the algorithm and it'll show you the angles for which the motors will move. But we realized that that's not very useful for someone who's using the robot arm. They should not care about what angles the motors move to, but rather that they actually move to it. So it's a higher level of abstraction, which we think is a good thing.
How about pressure, water pressure?
So the pressure, we currently have a 5-volt DC motor, and even with such low voltage, we're able to blast off whiteboard marker. So we believe that when this is put onto a larger scale at either 120 or 240 volts, it's going to easily be able to blast off any rust.
You all good, Andy? Yeah.
Yeah, I'm good. I'm good.
Yeah. Good job, team. I really like the way that you covered kind of the full range of functionality, and you went from kind of the UI to the the industrial mechanical design, and then showed some actual functionality of the various aspects of the product. I guess I had kind of two questions. I guess my first one was, as you were going through this, what was your biggest challenge? What was the hurdle that you had to overcome as you were kind of ideating through your solution?
I'm glad you asked that. So our biggest problem was getting the Arduino to talk in Python rather than C++. And the goal behind that was that rather than having part of our project coded in C++, part of our project coded in Python, and part of our project coded in HTML, and then you'd have whoever is having to debug it or update it in the future has to dip their hands in all three of them. We decided to put everything inside of the same document, same language. And it was extremely difficult because Arduino is made to talk to C++. So we had to find an extensive amount of libraries and even add some ourselves.
Nice, nice. Thanks. So my second question is a real quick one on the interface. You know, the demo you showed had users inputting coordinates for the area that they wanted to work on. Can you think of another way that you would allow a user to define the area?
So with the addition of a camera, because of our modular design, we could easily add a camera to it. And from there, they could take a picture and either click on where they would like to sandblast or where they would like the end effector to move to, or equally, we could add a rust detection software or anything of the sort to do it completely automated.
Nice, thank you. Yeah, thanks.
Thank you.
Yeah, I just want to add it. I like the idea of you know, multi-purpose use and to be able to add some additional features to it. So yeah, like a great great solution. The other question, just a quick one, I have like for you just mentioned the challenges on the programming. But is there any other challenges that you faced, like budget or anything else that, do you feel that you fulfill what was required based on clients' feedback?
I feel that we fulfilled all of the needs of the client, but with a greater budget, we definitely could have done more. We could have added the IR sensor we talked about, or we could have added the camera, and we would have been able to really bring a more full product to the customer.
Yeah, that's great. Thanks.
Thank you.
Okay, thank you, Team C10. So we'll go ahead with the next team, C12. So could you please share your screen, C12? Judges ready?
Yep.
Okay, so your time starts now.
All right. Good morning, everyone, and welcome to my GroupMates Now's presentation on a 3-degree of freedom robotic arm. Our group is named Droid, inspired by the robot named Droid. So to start, our client is the Department of National Defense, and what they've asked us to do is to build an autonomous and safe robotic arm that can paint logos onto the side of its Halifax-class steel warships. We've chosen to focus on the paint and effective. Now, obviously, one of the most important of this project is going to be safety, especially because a lot of people interacting with the robot, especially without prior knowledge, won't know how it works. We've broken up safety into 2 parts, when the robot is running and when the robot is still. When the robot is running, the most important thing is to keep people away from the robot because it is autonomous and therefore it does not need any manipulation while it is on. For that reason, we have floor marking tape to dissuade people from coming too close. If someone does get too close, or if the robot is malfunctioning, there is an emergency stop button on the physical arm that can be hit to immediately shut off the machine. When the robot is still, or when it needs to be moved, there are additional stickers and warning labels on any parts of the robot that may require more care, such as sharp corners or electrical parts.
As the main component of the robotic arm was provided, the focus was on the physical prototypes of the end effector. The end effector design was actually inspired by a drafting compass, such as this one. It's meant to hold objects such as markers, pens, pencils, or a paintbrush. In terms of user interface, the operator is to scan nearby items via Bluetooth. The Arduino is connected with the HM10 Bluetooth module that supports BLE, Bluetooth Low Energy. In this case, the Bluetooth is connected. The status of the connection is displayed along with a few pre-selected images. When clicked, the character is sent via Bluetooth to the Arduino to initiate the specific code for the image to be drawn. The e-stop is meant to terminate the code. Our solution provides a user-friendly experience for the boatswain, as it's a matter of a few clicks. The process is to simplify the following instructions displayed on the app, which does not require prior knowledge or any technical skills. The integration of Bluetooth allows for multiple drives to be in use, and the end effective design allows versatility in objects used for painting or drawing, such as a logo, and you could put in a paint roller in the main object. our project is just a scaled down version of the proposed project. Overall, an easy, simple, and adjustable product.
On the right-hand side of your screen, you're going to see a few things. So we have our working range of our robot plotted using MATLAB, and then we have our inverse kinematic solver. So given the end points or end coordinates, this code will solve where the motors need to go. And then you can see it implemented in Arduino. The video of the robot drawing the cross on the left-hand side is sped up to twice the speed, and you can see that the X, Y, and Z directions are affected. With this demonstration done, we'd now like to open up our question and answer period. Thank you so much for listening.
Okay. Question. Why Bluetooth?
When it comes to Bluetooth, the connectivity range is quite a reasonable amount, just because you're on a ship, on a boat ship, so the operator is able to be remotely far, just so the safety precautions are there. In case anything goes wrong, one, you have your emergency stop button, and not just that, you have a physical emergency stop button, so nobody gets hurt or anything like that. We'd like to avoid that. Not only that, but if we had a wired GUI user interface, that would cause many issues with like having wires and wire management and whatnot.
What was the distance from the user to the device? If you're going to utilize Bluetooth, what was when you're explaining that one, how far is the user from the device itself?
Our HM10 module was actually, we didn't fully test it, but it was around 20 to 30 meters of distance. So it is a reasonable amount of distance for a operator to operate the robotic arm.
In free space, or would there be obstructions? That's my last question. In free space or with obstruction?
It's
at 20 to 30 meters with obstructions?
Yeah,
there were some obstructions. Yeah, so sorry. So some obstructions, for example, one of us was like behind glass. Ideally, if we were simulating this in like an actual warship, there would be a controller managing all the separate painting arms, right? Because the goal of this arm is to free up boatswains. So ideally just be like one boatswain that's operating all these arms. It would be accessible in another room. Ideally, if we tested through glass and it still worked, it would be able to go through the walls of a steel warship.
In free space, the distance would be much larger, but it's not really viable in this product, which is why it wasn't mentioned.
Okay, thanks, team. I want to follow up on the wireless and just from a different perspective. I really liked in your presentation how you thought about the grader environment. You know, with the tape and the stickies. You thought beyond the product itself, which shows a lot of maturity in thinking about your design. Maybe if you could talk about the wireless component from a requirements perspective. How did you get to thinking that a Bluetooth or some other kind of wireless connectivity was the right way to go?
So I could go ahead and answer that. The reason we determined this as the product to go with is because the client wanted something easy to use for the boatswain, as they have it's expected to have a high school level of knowledge, and an app does not require much technical skills. You don't need a code, you don't need to do anything such that. So it's just simply, as long as you can use a phone, you can use the app to operate the robotic arm.
Mm-hmm. Okay. Nice. Thank you.
Yeah, I just want to add to Sean, I like your focus on safety. So you do have at the beginning very, like a few components that are focused on safety. And so the wireless technology also, it is in trend with the the industry trends, but also the multiple, like, I think you're the only team thinking of the many arms. So where is this idea coming from? Like, because other teams only focused on one arm, and why did you think beyond that and have ability to have control for multiple arms with this application?
So I can actually do a semi demonstration because I have the app right here. It's not, I don't have the arm with me accessible, but I can explain with my app demonstration. Here, just give me one moment.
And while Jabber sets that up, I can explain a little bit further. So we're not meant to control multiple different arms with just one app. What I was trying to explain was ideally, so since this whole project is based around the idea of like freeing up more workers to do other things, it'd be just like one person controlling a bunch of autonomous arms, just making sure everything's okay. And Bluetooth in our eyes was like the most feasible way to do that. So you don't have like the million wires running to a switchboard. You can just have like separate applications for each arm. Jara, go ahead.
So the concept behind it is basically when you're scanning an item, you have multiple Bluetooth devices that are present. Let's say you have two robotic arms, drawing robotic arms on the ship. This is robotic arm one, just for testing purposes. You press connect, and then you go ahead and send, let's say, the Canadian flag. It's going to tell you the input has been received. And after that, you could go ahead and stop your you don't have to stop it. You could just go ahead and disconnect. It's going to be autonomous, and it's just going to go ahead and draw the Canadian flag. And let's say you go to robot 2 here on my demonstration. Unfortunately, there's no input receipt because there is no Arduino to connect with. So that's just because that's why it's stuck. But like I said, you connect to robot 2 and you go ahead and do another drawing. And if for some reason robot 1, since it's disconnected, you don't have access to the e-stop button anymore, but you do have a manual switch. So if you're concerned about it going haywire or something going wrong, you just pull the switch. And then at the same time, robot 2 goes wrong, you have the e-stop button. Even though you're far, you have the e-stop button just to click it. So it's very versatile. It's easy to use and all of that.
Okay, great, thanks.
Just one comment, okay? Since you're the group who actually produced wireless communication, please consider other wireless communication standards aside from Bluetooth. Okay, the point there is there are other effects. Faraday cage, your 802.15.1 might not be that efficient when you're going to put it inside a metal cage. Okay, there are other standards. 802.15.4 will now be a consideration. Okay, any low power, low frequency will now be much better. Okay, so thank you. That's it.
Thank you. Bluetooth fit our purposes for minimum viable product, but we thank you for your comment.
Yeah.
Thank you, Group C12. So, Group C7, Spark Rangers, please be ready with your presentation. So this is the last group which will be presenting judges, and then we'll move you to the deliberation room, and the groups can interact with the clients.
C7.
Group C7.
I
Spark
can't share my
Rangers.
screen because the other person is still sharing.
Yeah.
I can't seem to unshare. Are you able to?
Yeah, you're sharing. Just
Spark Rangers.
Yes.
Okay. Can you guys see my screen?
Yes. Yes.
Okay.
Your time starts now, right?
Okay. All right. Hello, everyone. Today we're going to be talking about our 3 degrees of freedom robotic arm. We're Spark Rangers, who are Adriana, Newman, Aiken, and Anderson. For the problem statement, we decided to design a 3 degrees of freedom robot arm that will be used to do simple tasks for ships in a safe and efficient way. For the end effector design, we went for simplicity, and due to this, we decided to go for the paintbrush that is attached to a 3D printed G-clamp, as you can see in the design, that is attached to the robotic arm that does a back and forth movement to paint a designated area. For the movement of arm, we have 2 test cases.
For the first one, you can see that the arm moves in an XYZ coordinate once you put the designated coordinates, and the arm will use the inverse kinematic solution. For the second one, you can see that the arm is moving back and forth along the Z-axis to paint the designated area. And for this one, we know that the test cases were a little bit too small, so that's why it's kind of small, but you can see that in the UI later on. For the description, the code is written C++ and Python, which is the UI, which we'll get to later. Platform will be the Arduino software. For the hardware, we decided to go with a GRBL controller and an Arduino Uno. And as for the angle and like the inverse kinematic solution, we came up with an inverse kinematics equation on our own that we implemented into C++ later on.
Onto the UI and safety features. For the user interface, we use Thinker, a specialized Python program. Also, we utilize a software called PySerial to send data from Python to the Arduino IDE and then onto the board. As you can see, the UI is a rectangular box. We have the X, Y, and Z coordinate. The user can place any variables that they want, and they can press the submit button to transfer the data to the robotic arm. This will initialize the initial position of the robotic arm. Lastly, we have a red stop button. For safety, we have an emergency stop button. So if there's any technical issues or problems with the arm, the user can press the red button and all operation of the robotic arm will stop. This is a small video demonstrating this.
Why our product? We decided to go with our product because due to its simplicity and if its efficiency and time. So when talking about efficiency and time, we can easily say that C++ is the most efficient and fastest language, and whereas the Python would be the best UI environmental friendly, and therefore the workers that are working with this robot will be able to do this much efficient and faster. And as for the simplicity, I want to talk about our end effector. All you would have to do is just clamp it onto a 3D G clamp, and that will just be solve your end effectors issue.
Thank you for listening to our presentation. If you have any questions, don't be afraid to ask. Also, this is the resources that helped us make the code. So do you guys have any questions?
Okay, can you give me some innovation, since most of them are, let's say, off-the-shelf solutions that you had? Codes are or libraries are readily available. What innovations have you added to the entire project?
Okay, so we could say that first of all, we made up our Python UI ourselves. Let me show this here. Okay. So here's our Python UI and safety. So we coded this ourselves to have a user interface and a stop function ready. And this is the inverse kinematics equation that we solved ourselves. And as for this, here we can see that the inverse kinematics equation that we came up with, we written into a code. And after that, we with the help of the GRBL controller, we put it into a C++ code. And as you can see, it runs.
Also, we only use like the code that came with PySerial to send data from Python to Arduino as a basis. And then after that, we implement our own code over it.
Yeah, so we just import a package to for the transfer between code languages.
And the interface that you have, the UI, the how we call it, the dimensions are defined once you encode it in your, let's say, the UI that you have 1, 2, 3 will pertain to a point in space, XYZ.
Oh, you mean like the XYZ? Okay, so for this,
yeah.
You mean XYZ? Okay, so for this, for the UI, what we wanted to also put was for the XYZ, we can like actually like express like what X, what Y, and what Z could mean. So like in Z, we could say the rotation of the arm, Y would be the height, and length would be the X. So once the worker can see what they're working with on the wall in terms of painting, spraying, or whatever, they can actually just like implement it and use the conversion of like angles on the stepper motor with the centimeters to like identify where the designated area needs to be painted.
And they're in integers, right?
Yeah.
Integer values?
Yeah.
Okay. Okay.
Yeah, great job, guys. I want to talk a little bit about the clamp and how you, if you could talk a little bit about kind of the research that you did to drive you to the solution, that clamp solution that you you ended the product with.
Adrian, you want to take
So
the
I
lead?
can speak on that. Sorry, I have COVID, so my voice is a little messed up. So we went with the clamp solution because it's really easy. You just like twist the end to put it in the end effector. We originally thought of using like a spray gun, but it was quite costly to make. So we decided to scrap that idea and go with something easier.
Yeah, and here is our first like prototypes of the thing that we decided to use. But although because of the cost constraints, we decided to go with something way more simple and efficient. And I think that it actually turned out in a better way because now it's actually a lot simpler.
Yeah, love that prototype. So did you test your final design with other devices, with other than a paintbrush?
Yeah,
well,
so it works just as a G clamp in its name. Like you can clamp it to a table, you can clamp it to many objects. As long as the sides are flat, it works the best. But yes.
Which isn't the case on a pen, right?
And we would also say that the weight has to be like not heavy, like or like we would have like a constraint on the weight because if we put something too heavy, it would
Right.
the arm would not be able to carry it. Just to double make sure.
Yeah, nice. Okay, thank you.
Are there any other questions?
Yeah, great presentation, good solution. And my question is about using two programming languages. Like, how do you foresee the maintenance of these systems? Because you have Python and C++. So, like, do you foresee any kind of challenges with the, maintaining those two for user interface?
So we thought of actually coding the whole thing in Python at first, but we actually thought that was actually a worst case scenario because if we think about it, C++ actually is more a much more efficient and a faster language, and all you have to do is just import a PySerial package that would immediately like basically combine the code with one another. So I don't see us facing any challenges in terms of like using two coding languages.
Okay, that's good. Thanks for the answer.
So I think this is the end of the presentation. Thank you, group. So judges will move you to the discussion room, wherein you can discuss regarding all the presentations, and either Professor Rubina or I'll be there along with you. And client Theo will be here for all the participants. So client will be interacting with you guys on your projects. So first I'll just move the judges.
So I'll be joining the judges in deliberation room, and Pankaj, you can go back and forth between the two.
Sure.
First time.
This is being recorded.